So let me introduce the next presenter, Herbert Bernstein from Ronin Institute for Independent Scholarship. And Herbert will be talking about gold standard for macromolecular crystallography diffraction data.
Thank you. I'm sorry to have interrupted a very interesting talk. It was really quite nice. I'm going to be giving you essentially no pretty pictures. I'm going to be talking about that much neglected thing, metadata. We, for macromolecular crystallography, collect something between some tens of gigabytes to several terabytes for each data set, and we collect them very, very fast. We need to manage them very efficiently. And it wastes time if we get in the middle of a lot of translations of how we're looking at things. Now, this has been known for a very long time, but a miracle has happened. There's been a community agreement of how to organize our metadata. And I didn't come up with the term gold standard. Andreas Förster of Dectris said we should call this the gold standard for macromolecular crystallography diffraction data. And it really is turning out to be that. The agreement was reached in 2020. I gave you the reference for the published standard. And much to my surprise, much to my shock, this agreement is not falling apart. We actually have a worldwide agreement on how we should handle this. Okay. All right. Now, there are two formats that were in strong competition, HDF5 and CBF, both heavily used. CBF is the crystallographic binary format. That was adopted by Dectris for the Pilatus in 2007. Between 2007 and 2013, heavy use of that format, and it became the de facto standard for a lot of synchrotron data collection of MX data. But it was very, very clear that we didn't have enough performance, and the volumes of data required very good higher level packaging. HDF5 provides that. So in 2013, we came to agreement for the next major detector for MX called the IUCr on using a thin front end over HDF5 called NeXus. So the NeXus HDF5 format became the standard for the IUCr detector. We worked at combining the CBF format and the NeXus HDF5 format, and that's what became the gold standard in 2020. What's really important about this is we have a lot of data. It's very important data, but it's not just important to a few people. It has to be shared. It has to be distributed. It has to get reused. The FAIR principles of findability, accessibility, interoperability, reusability are critically important for macromolecular crystallography data. And this allows us to get much, much closer to wide, FAIR principles. Okay? Why are we doing this? Because macromolecular crystallography is the dominant means of determining the three-dimensional structures of biological macromolecules. Okay? Over the last few decades, most MX data have been collected at synchrotron beamlines using a large number of different detectors produced by what was then a wide range of manufacturers, taking advantage of various protocols and goniometries. And naturally, each detector manufacturer used the detector format that was best for their handling of data. This made reuse of data really, really hard. The gold standard facilitates, not will facilitate, facilitates the processing of data sets independent of the facility they were collected at. Now, look, there are just 32 major facilities, synchrotron facilities, but there's a lot of people with home labs that then need to process that data. And so, for fair, we need it. Now, the slide is slightly wrong. It's technically accurate, but slightly wrong. It says that what we're working with in all cases are one or more diffraction images. What we're really working with typically is, yes, we do some collections of one or more in order to set up a data collection. Typically, one collection will have several thousand to several tens of thousands of images. These are arrays of pixels, and we need to have for each array of pixels enough information to determine exactly where in the laboratory coordinate system each pixel is located. And when the intensity was recorded. The time is really, really important to us because we're facing continuous radiation damage. So you need to know when data was collected, not just where it was collected. And what we want to do is be able to locate the spots, index the spots, and integrate them. Okay. Well, we need certain metadata for that. At the very least, we need the detector distance, we need the detector orientation, we need the wavelength, we need the beam center. We mustn't lose this metadata. Well, in the past, we had a little problem. Okay. And that was the data and the metadata were not necessarily in the same place. The data was being collected, CBF or HDF5, and in the past in some other format. There even is still some use of TIFF. Okay? It's still there. But people would write the metadata in a lab notebook, would put it in an electronic notebook system. And while you were still at the same facility, well, referring to the data, referring to the metadata, the fact that they were in slightly different places wasn't a disaster. But certainly in the last year, even before that, crystallographers were becoming nomads, moving from facility to facility, and it very often was necessary that you have some data that was collected at one facility that would be processed at another facility or back at the crystallographer's home institution. And then it could be a disaster that the metadata was being recorded elsewhere. Okay? In the gold standard, the necessary data and the metadata are gathered together in some common container. Surprise, surprise. The common container that's heavily used at most of the major physics-oriented facilities is HDF5. It is a very, very good container. And I really do mean HDF5. I don't mean something which is sort of HDF5. I mean literally, with the software that goes with it. It's the format, it's with the software. That is the container. It's very, very important, okay? And then you can take this container of data and you can pick it up and you can carry it to another facility and you can put it on some common repository and stick it on Zenodo. And you can get very, very good ability of different users to use each other's data, the same user to use data that came from different facilities. Really, really helpful. Okay. We got this to work reasonably well for synchrotron data collection, and it is starting to work well for XFEL data collection. It is something which goes in successfully for dials, for XDS, for Mostrom, for HKL 2000, ZIA2, Autoproc, and eventually for Onda. This is something which saves tremendous time. And as I said, we are tight on time. Okay? Now, where does this come from? The discussion began in 1995. Andy Hammersley proposed the crystallographic binary format. We had a lot of discussion about it, and it was adopted. Not in 2005, okay? But it was starting to be used in demonstration stuff as early as 1997. That resulting format, IMAGE/CBF, okay, was adopted by Dectris for what was then the brand new Pilatus detector in 2007. That worked. Okay, it basically allowed the Pilatus to eat that market as being the right way to collect MX data. It became used not just as synchrotrons; it started being adopted by the home source people. Became used, but computing improved. Detectors improved, and the next generation of detectors, the IUCr detector, needed more. And as I said, we integrated CBF with HDF5, and that became what we're talking about now. Okay? And everything in that format still has an equivalent in IMAGE/CBF. And there's a reason for that. We need to be able to break stuff out for users, their home source, for their older software and for other software, so that they can still use things which got adapted to using IMAGE/CBF. So there's an interoperable format in 2 different presentations. Okay? There are slight nuisances. For example, the standard coordinate system in CBF and the standard coordinate system in NeXus essentially have a 180-degree rotation around the x-axis compared to each other. And there are differences. The differences matter. We try and be careful about it, make sure people don't make mistakes. But yeah, we live with 2 coordinate systems. Okay? If you are a crystallographer, you're going to start screaming at me, what about structure factors? Structure factors are very, very important. But when you live in the world as I do, where it's critically important that you are collecting the data before it becomes structure factors, it's just spots on an image. Okay? You tend to forget that ultimately what is needed for the final processing are structure factors. Well, we have a neat place to put it in both versions of the format. There's a reflection category and an extra reflections category. You put them in. I'm not trying to say they're not important. They are important. But from our point of view, they're simply derived data. I apologize. Okay? It's also important to know where and when the data was collected. It actually matters which synchrotron beamline was used and exactly when it was used. There are beamlines which do things that, like flipping their detectors around. And you need to be careful about that. That is important metadata, where you've recorded things. Okay? And time is really, really critical. As I said, we face radiation damage and we need to know when each spot was collected. Okay? So we take that. We then need to know where things are physically in the lab. So we record the experimental geometry. We record the experimental geometry. It's a long discussion here. Basically, it's the same thing as doing a robot arm. Okay? You have nested chains of axes determining the positioning of the detector, the positioning of the sample. And we simplified our lives. Exactly the same approach to recording that information, these chains of axes, is used in CBF and NeXus HDF5. We changed the NeXus approach to recording positions to record the same thing. You simply record a vector, which is the direction of an axis, and you allow an optional offset for the base of that, and you do chains of those axes. Okay? The general organization of it, we collect some groups. We have NX data, which contains NX entry, which contains NX data, NX sample, NX instruments, NX source. We have NX transformations in NX sample. We have NX attenuator, NX detector group, et cetera, in NX instrument. It's a very standard HDF5 layout. Okay. And if you look at the slides that I have posted, you will see the actual layout. But the important thing for you guys, before I run totally out of time, is I've given you the links for the availability of this. We have the definitions. There is samples on Zenodo, okay? And I promised you one last thing I was going to tell you what we're doing in the latest version of the software. In the latest version of the software, we are adding the ability to actually record as metadata the external links to data, sort of the opposite of going in the direction of VDS. And that is it. Thank you.
Thank you very much. Any questions for Herbert? It's nice to see fruition of all those long discussions, fighting, excitement about
peace.
CBF format.
We have achieved peace. We have
Yes.
achieved worldwide peace, at least in my little area of the world.
Yeah, knowing how much effort was put in it, that's really nice to see.
Well, thank you to the HDF5 group. Without the stuff you guys did, this wouldn't have happened.
Okay, there is a comment from Joshua. Let's see. Oh, I'm. So, from Joshua, yes, my goal in life to reach such a gold standard. Very impressive. From Rafael Girardot. So there are two file formats. Do you use a single API to read them?
All right. We use the HDF5 library as the HDF5 library. We use the CBF lib as CBF lib. The place where I bring together all the documentation is in the CBF dictionary. Okay, the software is moderately separated. For example, CBF lib uses the HDF5 library when it reads HDF5 files. So yeah,
another question
it's gathered.
What does the Golden Standard do in addition to the NeXus standard?
This has been adopted by NeXus, but this is something, basically NeXus is one entity, and then we have this world of macromolecular crystallography. And this is something which is under the IUCr, and has been agreement with the IUCr as well. So there's still CBF, there is still NeXus, and they are two interoperable standards maintained by two independent organizations, which, believe it or not, are at peace with each other.
Thank you. So we have probably room for one or two questions.
Okay.
Oh, yeah. Hi, Herb. Yeah, thank you. Thank you very much. Always nice to hear you. One question I had was, does the gold standard say anything about compression?
It doesn't directly say anything about compression, because this is still a contentious topic. Dectris still pushes BSLZ, bit shuffled LZ4. Okay. My personal experience and experiments says Z standard would be a better choice. It's both more efficient by some cases 30% and faster. Both are in fact supported by the HDF5 library through plugins. But you need to be careful. You don't want to ship data to people with a compression they're not expecting because they don't have the, that plugin available. So politically, officially, the answer is BSLZ4. My personal opinion is all should move to Z standard. Everybody. For everything. Okay. I've been a bad boy saying that.
There is one more. Going back to API, does it mean that every application that needs to read access the files has to have the two specific format codes?
As far as I'm aware, nobody is running a major beamline who does not have the ability to read both formats. in terms of minimal technical requirement, one or the other would do because you can translate between them. For efficiency at a major facility, I highly recommend stick to HDF5. If you're sitting at a home lab with some software that simply believes in CBF, fine, use a CBF copy.
Thank you. We need to move to another talk. There are still questions in the chat room, but we'll try to answer and post them. Thank you very much.